Good afternoon, folks. We'll go ahead and get started. So the first thing is me to get the actual PowerPoint on the screen in order you can see it. It's pretty important that if things don't work, like the PowerPoint doesn't show up on your screen, that you let me know. So you need to let me know if you have questions or if there's issues with the screen being able to see or hear me. So today we're going to start Electricity 1. We have 5 classes on electricity. This is the beginning class, and we'll take you, if you go all through all 5 sessions, all the way up to 3-phase electrical systems. So it's a pretty good process to go through. Again, we have problems to do, and anytime that you see me doing a problem, understand that I do these problems as I go along. I found out if I have them worked out already, that I go too fast, so I try to slow down, which makes me prone to error. So if I make an error in calculations, I would much prefer you tell me during the class that I made an error in calculations than later telling me after the class and everybody thinks that they don't understand, when in actuality I couldn't add 2 plus 2. So let me know as we go along if you have questions. This is your class, and we want to make it as beneficial for you as possible. So we're going to start out with some basic fundamental properties, and that's called Ohm's law. And we have this concept where effect is equal to cause versus opposition. And so right here, we have an effect of where amps are flowing through this wire, or at least he's trying to. And that we hope that's the effect. And the cause, the culprit behind this is Mr. Volt himself, that's doing the pushing. He's pushing the pressure. And then the guy that's opposing that pressure and this effect is Mr. Ohm, which does not like to see anybody flowing through his wire. So those are the 3 components. Now, I've laid out 3 different equations that deal with current in amperes, volts, V, and resistance, ohms. Okay, so this would be the effect, or the effect is the actual current in amps. The cause is the volts, and then the resistance is the opposition. So if I look at that and look at that equation, that's where I start with my very first equation known as Ohm's law, which says that the current is equal to the voltage divided by the resistance. Again, this is the pressure, voltage is the pressure, and the resistance is the opposition. Well, that's okay if I'm trying to solve for current in amps, but I can solve for voltage, and so voltage is equal to current times resistance. And that's the equation that I try to remember for Ohm's law, V equals IR. So that's a very simple solution from this original equation, I equals V over R. I just basically multiply both sides by R, and I've got V equals IR. But sometimes I have to solve for the actual resistance that I've got. And so that would be resistance is equal to voltage over current. So you've got to remember one of these. This is the one I remember. And from that one, you need to be able to derive the other 2, because we're really not sure on a daily basis on what element or what portion of this Ohm's law are we trying to solve for. Now, I will make a statement here that V equals volts. Technically, that V would be voltage drop. And if I were to have a source, I would designate that as E. That's my source. Now, after I told you the correct way it should be done, I will also let you know that 99% of the time, I just use V for volts, whether it's a source or a voltage drop. I never could see the merit in having the E sign there. But typically in industry, or a lot of times in industry, you will see that E given for the source voltage, like if you have a battery or a generator supplying this system. So with that in mind, we need to define polarities. And we need to understand that when electricity all came about and Benjamin Franklin was doing his keen thing with the kite and the key and the thunderstorm and all those sorts of things, they did have an idea about this effect equals cause over opposition. They had that idea, but they really had no way of actually monitoring the electrons flowing. And so this current in amps is actually a measure of electrons. So we're actually seeing electrons moving in a conductor, and the measure of those electrons turns out to be current in amps. So before we could actually see those electrons moving, we already had some equations set up. And so what I'm going to show you is what is industry standard. And so for a load, a resistor, it cannot provide any energy. It can only eat energy. For this load, we are given definitions that as the direction of the current, as current enters the load, that's the positive terminal. The negative terminal is where current leaves the load, okay? So in this direction, I'm showing current, and I see a positive and negative. As I told you, we guessed on the direction of these electrons flowing. And in fact, we guessed incorrectly. I guess we didn't guess. It was some old guy along before I came along, but they guessed incorrectly. Electrons are actually flowing the other way, but by the time we decided that electrons were actually flowing the other way, industry standard had taken place, and this is what we live by. Certain entities, like the military likes to show current flowing the way the electrons actually flow. So they would show it the other way. No problem in answers. They're very consistent about it, but this is the way that we will deal with it for our lives and for our career. Current enters the positive terminal of a load. If you'll notice, I've drawn that same resistor here, but now I have current going this direction. And when current enters the load, that's the positive side of the load. So voltage would be positive to negative. So again, in a load, current enters the positive terminal of a load. Now, in a source, this is my source right here. I have a diagram. This symbol is the symbol for a battery. So I have a battery here. I have a DC battery source. It's a source of energy. Current always leaves the positive terminal of a source. So current leaves the positive terminal of a source. Current enters the positive terminal of a load. That's our definition. Now, understand that sometimes we have to charge a battery. So if we have our battery on a charger, like our car battery is in the car, and after we start the car, the alternator kicks in, and it's actually providing energy to the battery to store it back up. In that case, the battery is no longer a source, it is a load. Because guess what? Current is entering the positive terminal of the load. So when the battery is being charged, it's no longer a source, it's a load, and current would be entering the positive terminal. Any questions over that? Any concerns over that? Those defined polarities are going to be important for us going throughout all 5 classes of electricity. So down below, we have a real small example here where I've got current entering into a resistor. There's my positive terminal. Current enters the positive terminal of a resistor, always enters the positive terminal resistor. I have 16 volts dropped, and the resistance is 2,000 ohms. So I go back to my equation that I remember, V equals IR, and I know the voltage is 16 volts, and I know that the current is, I don't know, and the resistance is 2K ohms, or 2 times 10 to the third. So I divide both sides by 2 times 2K ohms. That gets rid of it on this side. So I find out that my current is actually 16 volts divided by 2 times 10 to the third. So remembering back to our math class, 16 divided by 2 is 8. And 10 to the 3, bring it to the top, is 10 to the minus 3. And so in this case, the current flowing through that resistor would be 8 milliamps, or 0.008 amps. So that would be the solution to that very basic, simple problem. So let's look at a few examples here. Let's determine the current resulting from an application of a 9-volt battery across a network with a resistance of 2.2 ohms. Notice how I like to make the verbiage long because I want to confuse people when basically all I'm saying is, come on, give me Ohm's law. So again, I go back to my version of Ohm's law, V equals IR, and from that I derive current's what I want. So current's going to be equal to voltage divided by resistance. So here we go. I've got that equation. I've developed that. The voltage is 9 volts and the resistance is 2.2 ohms. So 9 divided by 2.2 ohms is 4.09 amps. So in this circuit, I've got 4.09 amps that's flowing continuously in the circuit. It leaves the positive terminal of the battery. It enters the positive terminal of the load, and it comes back over here and it enters the negative terminal of the battery so it can leave the positive terminal battery. So I've got this circulating 4.09 amps continually circulating in this circuit until the battery eventually goes dead. But in theory and in heaven, I've got a great battery and it will last forever. Example number 2. Calculate the resistance of a 60-watt light bulb if there's a current of 500 milliamps. Resulting from a voltage of 120 volts. Well, we haven't talked about wattage yet, and we'll talk about that later in this class. But I did give you some information. I give you current and I give you voltage. So I go back to my equation, voltage equals current times resistance. Now I have to solve for resistance, where that is resistance equals voltage over the current. And that's the equation I've got. Well, here again, I've got 120 volts. That's right there. And 500 milliamps. Notice how quickly I went to times 10 to the minus third. Well, 120 divided by 500 is going to be 2.240 times 10 to the third. Because I changed the sign when I brought it on top, as we talked about in math class. So 0.240 times 10 to the third, move the decimal point over 3 places, and that's 240 ohms as I drop the 10 to the third and bring it down. So I can determine what the resistance is of an item if I'm given the voltage and the current. Problem number 3. Calculate the current through a 2 k ohm resistor if the voltage drop across it is 16 volts. Well, that looks awful familiar, doesn't it? That looks like the example I worked out 3 slides ago. 16 volts divided by 2 times 10 to the third. 16 divided by 2 is 8. Bring the 10 to the third up on top is minus 3. So that's 8 milliamps. Easy problem once again. Example number 4. Calculate the voltage that must be applied across the soldering iron to establish a current of 1.5 amps through the iron if the resistance of that iron is 80 ohms. So I'm going to go ahead and start drawing circuits here. So now I'm going to have some voltage applied. Notice I called it E because that's the correct way to do it. And it's going to go through some soldering iron that I'm going to represent as a resistor. And the resistor is 80 ohms. And this is the positive terminal of the battery. This is the positive terminal of the resistor. And current is going to be flowing this direction. And I know that that current is 1.5 amps. That direction. So going back to my basic term, V equals IR, says that the voltage is going to be equal to 1.5 amps times 80 ohms, and that equals 120 volts. So I can determine what the voltage is that's applied across that battery. Okay, one more example before we move on to something a little more elaborate. You've just performed an insulation resistance test. And for those of you that are new, you just did a Megger test. You just performed an insulation resistance test on an open 13.2 kV breaker with your 10 kV Megger. The Megger was set for 10,000 volts, and the resistance that you read was 30 gig ohms. And that happens pretty often. So you're doing an insulation resistance test that we often mistakenly call a Megger test. You've applied 10,000 volts, and the insulation resistance that you received back was 2 gigaohm. Well, what does that really mean to me? Well, again, solving for I get current equals voltage divided by resistance. So the voltage was 10 times 10 to the 3. That's my kV. And my leakage reactant, or my resistance, was 30 gigaohms. That's 30 gigs. That's 10 to the 9th. So I've got 10 divided by 30. That's 0.333. And I got a plus 3. And when I bring the 9th up to the top side, that's a minus 9. That's times 10 to the minus 6th. So the actual current that's happening in this circuit is 0.333 microamps. And so what your test set is actually looking at, your test set is actually reading the current, and it's doing a mathematical calculation to determine what the resistance is. It didn't read resistance, it actually read the current. It supplied a voltage, read the current, calculated a resistance. So this is 0.333 microamps. I don't like seeing the decimal point there, so I'm going to move the decimal point over 3 places. And when I do that, this was 0.333 times 10 to the minus 6th. And when I move it over 3 places, that makes it 333 times 10 to the minus 9th. And so actually, this is 333 nanoamps is what the current actually is flowing through that open breaker. So any questions with that, folks? You guys okay with that? So should have a basic understanding of Ohm's law, the kinds of questions that could be asked with Ohm's law, and how it actually applies in this circuit. And in this circuit, basically what I've got a 10,000 volt battery, plus and minus, and I'm going through this open contact in the breaker that has some resistance there, and that resistance was 30 gig ohms. It's always going back to this very basic circuit that we started at with the very first one. Now, I realize that the breaker doesn't look like a resistor, but there is some resistance there, or I wouldn't be reading that kind of current. Okay, so we've got Ohm's law down now, I hope. Voltage equals current times resistance. But that's not the only thing we need to worry about. We need to worry about this term called power. Power is an indication of how much work can actually be accomplished in a specific time. And that work is given in the terms of watts. When you buy an old 60-watt light bulb, that is the definition of how much heat is given off. That's the work that's given. So it's the rate of doing work, and that's what we measure work in, the ability to do work in electricity. The basic equation for that is power in watts is equal to voltage times current. And that's the basis that we're going to use for all 5 classes in electricity. We're going to add some more terms to it later on, but that's what we're going to go with. But I also want you to understand that if I look at things, I can say, you know what, I don't always know what the voltage is and the current is. But I can go back to these other equations where what? I was equal to V over R, and I knew that resistance was equal to V over I. So those are a couple of things I can use. So in this one, if I did not know what I was, I can say VI is the same thing as what? V, and this is by definition I, times V over R equals V squared over R. Hence, the second equation. If I didn't know what voltage was, I can come back to VI, and I can say VI is equal to what? I don't know what voltage is, but I can know what some other things are. And so resistance is equal to V over I. So I can put R times I squared, and that will equal the same thing. I can make the same derivation here, where R is equal to V over I. And so if I have V over I, and I have I here, and I have to have, so this is resistance, so I have to have another I on top of it because I added the I down here in the bottom, so I can come up with I squared R. I squared R is another way of calculating wattage. So power delivered is equal to voltage times current, and that's in watts. That's how much a source delivers. Sometimes we rate electrical equipment like a motor in horsepower. And there's a little conversion where 1 horsepower is equal to 746 watts. So that will permit me to do things with horsepower as well. So let's see if we can look at a couple of things with regard to power. A DC motor is supplied by 120 volts and draws 5 amps. What's the power delivered to the motor? Well, here we go. I'm still back in the same circuit that I've had all along. I have a 120 volt battery. Yeah, somebody have a question? Okay. I have a 20 volt battery, and then here I have a motor, and it draws 5 amps. Well, E equals VI. 120 volts times 5 amps is equal to 600 watts, or 0.6 kW. We seem to like to use the terminology kW. So I can figure out what the power delivered to that motor actually is. What's the power dissipated by a 5 ohm resistor if the current is 4 amps? So here I have this resistor, 5 ohms, and I've got 4 amps going through it. Well, this is where I would use this equation, I squared R. 4 amps squared times 5 ohms is 80 watts. So that power that resistor is dissipating, the heat that's giving off, would be 80 watts worth of energy. Sometimes the power is given and the current or voltage must be determined. So let's look at that. So if I know this, that power is equal to I squared R, and so solving for I squared, that's power divided by resistance, I can come up with an equation that if I'm given power and resistance, I can determine the current because it's the square root. I know that V squared over R is equal to power, so V squared is equal to PR. And so therefore V is equal to the square root of PR. So I can solve for every aspect now in power and in Ohm's law given two quantities. I can do the work. I can make the solution. So the last example here before we actually go to the homework is to determine the current through a 5K ohm resistor when the power dissipated by the element is 20 milliwatts. Okay, so I've been given resistance size, and I've been given power, and I want to know what current is. So that goes back to this equation, power equals I squared R. I know this, and I know this. So I can solve for the current. I squared is equal to P over R, and the power was 20 milliwatts, 20 times 10 to the minus 3. And the resistance is 5,000, 5 times 10 to the plus 3. And so I also can take the square root on both sides and solve directly for I. So here's my 20 milliwatts. There's my 5K ohms. 20 times 10 to the minus 3 divided by 5 times 10 to the plus 3. 20 divided by 5 is 4. I take the plus down here, bring it on the top, and make it a minus 3. So that's 4 times 10 to the minus 6. Square root of 4 times 10 to the minus 6. And the square root of that is 2 times 10 to the minus third. 2 milliamps worth of current. So that's the end of the lecture today. And so I want to spend the rest of the time actually working some of the homework problems if we can. So I'm going to put this down back where I had it. And I see I've got a few more people in here. Okay. And I'm going to go to my whiteboard. And so now I've got my whiteboard. So let's look at the problems that I gave you. We're going to do like the first 5 if time permits. So problem number 1 was, what's the potential drop across the 6 ohm resistor? So I've got a 6 ohm resistor, and I've got current flowing through it, and it says I've got 2.5 amps. So this resistor is 6 ohms. So I know that plus is here because current's entering the positive terminal. And so what's the voltage drop? Well, that's the very first equation we said. Voltage equals current times resistance. I had 2.5 amps. And my resistance was 6 ohms. So 2 times 6 is 12, and half of 6 is 3, so that's going to be 15 volts. Okay. Problem number 2 in our homework. A refrigerator draws 2.2 amps at 120 volts. So I go back to my 120 volts. Not very realistic because I don't have many DC refrigerators. 120 volts plus or minus. And now I have over here a refrigerator, and it is drawing 2.2 amps. So, want to know what the resistance is? Well, I got to go back and solve for resistance. Resistance equals voltage divided by current. And in this case, that's going to be 120 volts. Divided by 2.2 amps. So 120 divided by 2.2 turns out to be 54.5 ohms. So that's what's supposed to happen. So one of the things you'd do if this refrigerator wasn't working or something was happening, you would disconnect it and put your ohm meter there, and you should read 54.5 ohms. If not, then things aren't working like you thought they should. Number 3, at starting, what is the current drain on a 12-volt car battery? So I've got a 12-volt car battery here. And I'm going through the starter of my car. And it's telling me that the starting motor has a resistance of 0.056 ohms. So now I got to solve for current. So current equals voltage divided by resistance. So I got 12 volts divided by the resistance of 0.056. And so when I do that math, that turns out that I've got 214 amps, 214.3 amps, which is the reason when I go to buy a battery, I buy a battery that's got cold cranking amps of somewhere 500 to 600 cold cranking amps, because When it's cold outside and this motor doesn't want to start, it doesn't want to turn over to start with, and it's got a low resistance, it's got an unbelievable amount of current there that it wants to use. Number 4, the internal resistance of a DC generator is 0.5 ohms. Determine the loss in terminal voltage across this internal resistance if the current is 15 amps. Okay. So this one gets us a little further along. So I have a generator here that I bought. It's not a perfect generator. Because inside this generator is some internal resistance, because there's a wire inside that generator, and that makes up resistance. So the actual generator would be what's inside this box, and the imperfect part of it is this little resistor. Well, I told you that the generator is plus and minus, and it was determined that this generator had a plus and minus, and it's putting out 15 amps. Okay? And it told me that this internal resistance is 0.05 ohms. So what kind of voltage drop do I have across that? Voltage equals current times resistance. I've got 15 amps. And I've got an internal resistance. Come on, pen, work for me. I've got an internal resistance of 0.05 ohms. So 15 times 0.05, I'm sorry, it's 0.5, 105. You guys need to catch me on that, 0.5. So 15 times 0.5 is 7.5 volts. So in this little internal resistance here, I had 7.5 volts dropped. That's the loss. So if this generator were, let's say it's a 120 volt generator, then my output terminals right here, from here to here, at 15 amps, won't be 120 volts. It'll be the 120 volts minus the losses here, 7.5. So it'll only be 112.5 volts. Not near what I want to be perfect. So I would pay extra money for a generator that had a lower internal resistance, which is exactly why you pay extra money for a high quality generator. You don't want those losses internal to it. Okay, number 5. We're going to do 5A, just the 5A portion, because we haven't lectured about 5B. An electric heater draws 9.5 amps. So a heater I'm going to represent as another resistor, and it draws 9.5 amps. What else do I know? It's connected to a 120 volt supply. Plus and minus, plus and minus. What's the internal resistance of the heater? Well, solving for resistance. Resistance equals voltage divided by current. I have a 120 volt source. I've got 9.5 amps. So 120 volts divided by 9.5 says I've got a resistance of 12.63 ohms. So that's what the resistance of that heater would be. So we're going to build on from this portion, from this example next week, when we start talking about actual energy. And we'll be discussing the watts here. So the next session, we'll use the same PowerPoint and the same questions. We'll go on and finish the rest of the problems, but we're going to get into power and the kilowatt hours, the measurement of energy that you're paying for on your electric bill every month. So, any questions? Any concerns?
No.
So we're all good. All right. I thank you for your attention. Thank you for being part of this today. We'll see you next Monday at noon, same